Good morning, everybody. Can you hear me?
Good morning, Victor. Yes.
Good morning. Okay, there seems to be some technical problem with our Blackboard LMS. So I thought we can have today's class through Zoom. Hopefully this will be clear. So I hope all of us, all the students know about it. We have to have another 7 members. So let us give some time for them to join. Who is ASUS ASUS?
Khulud.
Yes. Oh, Anand. Okay. Yeah, while we wait for others to join, do you have any questions, any of you, please? Yes, Ragat, Vada, any questions?
Doctor, morning, doctor.
Good morning.
Doctor, I have a question regarding our project.
Your project. Yeah, please.
Yeah.
What is it?
I want to ask if my project is about certain diseases.
Okay.
And in the first point, I have to calculate the mean for each of them, each disease individually, or all of them.
Now, if you have got sufficient data for various periods or for various locations, or if you have got a number of observations for each disease, you can go for each disease, and the mean for each disease can be calculated. Similarly, if you have a number of diseases, you can have an overall mean also. So there is no hard and fast rule as to how you should go about. So basically, it depends on what you want to do. Are you looking at the average number of patients having any disease, or a number of times a particular disease is repeating, or then you can go ahead and compare whether a particular disease is having an average which is more than the overall average. So in that direction, you can think of.
Okay, thank you.
Okay.
Yes.
So look for some data, and based on the data, try to formulate certain, let us say, the descriptive statistics, and look for some inferential statistics. Maybe if you are having the values to be compared with one value, maybe some hypothesis testing procedures, or if you are looking at the relationships, maybe your correlation and regression analysis. So that way you can think over. This applies to all of you. Is it clear? Any more questions?
Morning, doctor. I'm writing in the chat part.
Okay,
I'm
discussion
not gonna...
3, question 8. Okay, let me try to share the discussion 3, question 8. Let me open that. Can you see this one? Is this your question? Is this your question? Sarah?
Doctor, I'm using the chat. I'm
Okay.
writing.
Now I'm sharing the screen. Are you able to see the screen?
Yes, doctor.
So I think your question is question number 8, isn't it? Given Z is a standard normal variable, the value of Z for which Z less than or equal to Z is 0.2580. Is this your question?
Yes, doctor, this is the question. When I did the calculation and I used the Z table, I got 0.7, but the answer said minus 0.65.
Basically, you are looking at the value of Z so that the area below Z is 0.2580. Are you with me? The area below the point is 0.2580. Are you clear? So let me try to share my whiteboard and try to write down. Okay, we want probability of Z below the value Z to be equal to point. What is the value? Anybody? What was the probability in the question? 0.2580. Isn't it? So what I am trying to do is, I am trying to look for okay. So I'm trying to look for normal distribution, okay, which means 0. Are you with me? And I want the probability, the point Z in the distribution, so that the area below this, are you with me, is point this value, 0.2580. Are you clear? I am trying to find this area, the shaded area. This area must be 0.2580. Now note that my tables gives me the area between 0 to Z. This is the area given, isn't it? This is the table value. So I can get this value, the area from 0 to, because the value is 0.2580, basically the area is less than 0.5. That is first thing you must know. Are you with me? The area is below 0.5, so the area will be, the value of Z will be on the negative side. And I can get this value. What is this value? It is 0.5 minus this value. So it will be 0.5 minus 0.2580. Can you tell me what is this value? I think
0.242.
2420. So I will get the value of this area to be 0.2420. So look for your tables where you will get the area as 0.2420 and it will be a negative value. Are you clear? Are you with me?
Yes, with you, doctor.
So it will be a negative value, it will be minus Z actually. It will be negative where the area is 0.2420. So look for your Z table. I hope you have got your Z table. Where is your area? 0.2420, 2420. It is 2422. It is there at 0.65. Clear? So 0.65 gives 2422, which is close to 2420. So this will be minus 0.65. Are you with me? Is it clear?
Yes, clear.
So that is the answer we had got.
I have another question. It's question 12. It's asked to calculate the mean. When I calculate the mean, I get the answer 2.5, but it says it's 0.72.
Question number, is it the same?
The same discussion number 3, yeah.
Okay.
Question 12.
3. Okay, let me stop sharing. Again, go to share screen. Discussion number 3. Okay, question number 12.
Yes, number 12.
So you are given a company studying the number of monthly absences among 125 employees. The following is the probability distribution of likelihood that people will absent for 0, 1, 2, 3, 4, 5 days. Okay. So you are given the number of days of absence together with the probability of absence. Here. So what is the mean number of days of absence? So what is the formula for the mean? What is the formula? It is sigma x px. Multiply x is the number of days of absence. Probability of absenting for 0 days is 0.6. Probability of absenting for 1 day is 0.2, like that. So you multiply x times px, means 0 times 0.6 plus 1 times 0.2 plus 2 times 0.12, 3 times 0.04 plus 4 times 0.04 plus 5 times 0. So that will give you the mean. I am using the formula sigma x px. This is a probability distribution for a discrete random variable, isn't it? Is it clear? Are you with me?
Yes, doctor.
So just multiply the values taken by the variable with the probabilities and add them, you will get your mean. Maybe you can recalculate and see what is the value. You must be able to get the value, or whatever value you get will be the right answer. I think it is 0.72. It may or may not be. So just multiply the value 0 times 0.6 plus 1.02 plus 2 times 0.12, like that. Okay. Is it clear? Yes or no? Does it answer your question?
Yes, doctor. I'm using the text box, the chat box there.
Chat box. Okay. Yeah. Chat box. Okay, good. Yeah, any other questions, please? So shall we go back to what we were doing in our last class? What were we doing? Is this the problem we were looking at? We are going through the steps in hypothesis testing, if I remember, isn't it? Adrian, Mariam, Reem.
Yes, doctor.
Yes, doctor.
So what are the steps in hypothesis testing? Can you tell me briefly? Anybody?
Do you want me to read it?
You can read it or you can tell in your own words. What are the steps? That's all. What is your first step? What is your second step?
Okay, I can read it. The men of a certain age have
No,
a
I
mean
don't
weight.
want the question. I want what are
Oh.
the steps in hypothesis testing? How do you proceed with hypothesis testing? You define the null hypothesis, you define alternate hypothesis, then
Calculate test statistic.
yeah, before that, do you do anything else?
Collect data.
Collect data, okay.
Compare value and conclusion.
So you collect the data, okay. Let me put it more systematically. Define your null hypothesis and define your alternate hypothesis. Null hypothesis is represented by H0, alternate hypothesis is represented by H1. How do you identify the null hypothesis? What is the speciality? If you are given two hypotheses, let us say here we have got two hypotheses, mu equal to 170, mu greater than 170. How do you say this is your null hypothesis and this is your alternate hypothesis? What is the thumb rule?
The null hypothesis has an equal in it.
Yes. So the hypothesis which contains the equality is always your null hypothesis. So the alternate hypothesis and the null hypothesis are complement. So if the alternate is greater than, the null hypothesis can be equal to or even less than or equal to. Both are right. So when you have got a question, the question gives you one of the hypotheses. So here we are given the men of a certain age have a mean weight of 170 pounds with a standard deviation of 65 pounds. So you are given the value of mean mu and you are given the value of standard deviation, that is sigma. An observation was made in the city's neighborhood and 400 men in the neighborhood were selected. So the sample size happens to be n to be equal to 400. And the mean of these 400 people was found to be 178 pounds. So this is the value of your sample mean, that is your X bar. Can we conclude that the diacetyl system in the neighborhood will improve the mean weight? So when we say that, the question says that whether the mean weight is improved, means actually this means whether mu is greater than 170. So this is what is given in the question. So because this is given, we can write down the complement. So mean height improve. Improve means more than. So it is strictly more. So improve means strictly more. So I am writing down H1. I am taking the complement and I am writing down the null hypothesis. Now by looking at the alternate hypothesis, I will say whether it is a one-tail test or a two-tail test. Isn't it? So what is next thing? I define whether it is a one-tail test or a two-tail test because it is strictly greater than, I know that it is a one-tail test. Very clear? So because it is a one-tail test, what I will do? Next I will go for looking at the rejection region. Because it is strictly greater than, I will reject, the rejection region is on the right hand side. So this is my rejection region. So I will define my alpha and I will look for my area beyond the Z alpha to be equal to alpha, and I will get the value of Z alpha using my Z table. Because sigma is known, I use my Z table and I know what is the formula I have to use, isn't it? So next step is step 1, define H0. Step 2, or let us say define H0 and H1 and define whether it is a one-tail test or a two-tail test by looking at the alternate hypothesis. Then draw a graph and mark the rejection region. Having marked the rejection region, you define alpha. If alpha is given, alpha is not given in the question, so I take it to be 5%. So if alpha is not given, I will take it as 5% or 0.05 and I get the Z value using my Z table or Z of, that is the critical value, the rejection value. So the critical value I get from the table of Z distribution because sigma is known. The standard deviation of the population is known. So I will arrive at the test statistic. That is my next step. The next step is calculating the actual Z based on the samples. So we have taken a sample of 400 people and we have looked at the mean for the 400 people and we have made use of the formula for the samples, the test statistic. What is the formula? It is nothing but the standardized value for the test statistic. It is nothing but x bar minus mu by sigma by root 10. So calculate the test statistic value and arrive at the test statistic. Is it clear? So arrive at the test statistic. Okay, this is already there. So we arrive at the test statistic, which is x bar minus mu by sigma by root 10. So calculate the value of the test statistic. The value of the test statistic happens to be the value by using the formula. So make use of the formula. X bar is 178 minus mu is 170 by sigma by root 10. Okay, so we have defined the value of alpha is 5%, and from the tables I get the rejection region, that is the value of z alpha to be 1.645. The value of test statistic happens to be 2.46 because 2.46 lies in the rejection region. It is more than 1.645 to reject our null hypothesis. Are you with me? So these are the
Yes,
steps
sir.
we have made use of to arrive at the conclusion. So what is the conclusion? Based on the sample of 400 observations we have calculated, we have considered, we arrive at the conclusion that we reject the null hypothesis and state that the average value of mu is greater than 170. Are you clear? So that is one way of arriving at the decision using the steps in hypothesis testing, where we have made use of the table, the Z table for arriving at our 1.645. So this value 1.645 we arrived at by using our Z table. Do you remember? By using the value of alpha, we got this 1.645 using our Z table, and we arrived at this value 2.46, which is the test statistic value. So we calculated the value of test statistic and we arrived at the value as x bar minus mu by sigma by root 10. It is 2.46. So here the procedure consists of having your tables, whether it is Z table or any other table, to arrive at the rejection region, and also to have your test statistic formula. X bar minus mu by sigma by root 10, or T statistic means x bar minus mu by s by root 10, whatever it is. So you need to have the formula with you, you need to have the tables with you, and you have to calculate the value of the test statistic and compare with your critical value. So this is the procedure which we follow, which is a bit laborious, wherein we are looking for the formula and we are looking for the tables and we are computing the value and getting the values from the table and comparing. But nevertheless, this is one of the procedures. The second method for arriving at a decision is what is called the p-value, using the p-value method. Let me clear all drawings. Okay. So we'll make use of what is called the p-value method. What is p-value? P-value is nothing but the probability of getting an observation or based on the test statistic, which is as extreme or more extreme than the value we have got. That is, whether we are trying to see whether based on the sample, whether there is a sample evidence to either reject the null hypothesis or do not reject the null hypothesis. So that's what we do basically, isn't it? Are you with me? Let me make it more clear. Now, we are rejecting the null hypothesis because our test statistic value is 2.46, which is greater than 1.645. Isn't it? So what is happening here is We are trying to look for the test statistic. The value of, let us say, this is the alpha. The value of this was 1.645. The area beyond this 1.645 was alpha, isn't it? Are you with me? This was alpha. What was the value of alpha? It was 0.05. Is it clear? Sahar, Manahal, Reem?
Yes, doctor.
Okay. Then what we did, we looked at the Z statistic. What was the Z statistic? It was 2.46, which is more than 1.645. Can you say this? The red mark. Let us say this is the test statistic. What is the value? The value we got was 2.46. Okay. Now, what is it? This 2.46 is based on your sample. Do you remember 2.46? We calculated as a formula x bar minus mu by sigma by root n, where x bar and n were based on our sample. So the test statistic is based on the sample. So the p-value is nothing but the probability of getting a sample such that it gives a value which is equal to this particular value of test statistic or beyond. In other words, we are looking at this probability, the probability of having the test statistic to be 2.46 or more. Are you with me? This red area, we call it as the p-value. Is it clear?
Yes, clear, Professor.
So p-value is probability of observing a test statistic at least as extreme as the one computed, that is as extreme as 2.46 or beyond. When we know that the null hypothesis is true. So that's how the p-value is defined. In other words, what the p-value is nothing but the probability of having a sample which is having the test statistics to be 2.46 or more, which is on hand or more. In other words, it is the area beyond your calculated value. Are you with me? Ulud, Hind, Ragad?
Again, doctor, sorry.
We have got two probabilities. One probability is 0.05, which is nothing but our alpha. Okay? 0.05 is nothing but our alpha. This is the value of alpha. So alpha was 0.05, and based on that, we got this 1.645 using your table. Is it clear? Are you with me?
Yes, doctor.
Okay. Now what I do is, we have calculated our test statistic based on the sample, isn't it? We have made use of the sample and we have arrived at the test statistic as 2.46. So we compare 2.46, 1.645, because 2.46 is in the rejection region, that is more greater than 1.645. We rejected H0. If it was less than 1.645, we would have accepted H0. Are you clear? Okay. Now what I do is, I calculate the probability of getting a value which is equal to or greater than this calculated value, that is 2.46 or more. That is, I will try to look at the area beyond 2.46 in your normal distribution. So if the value of P is less than 0.5, then it will be in the rejection region. The Z value calculated must be in the rejection region. Are you with me? Compare the area of red one and blue one. If the red area is less than blue area, naturally the value is less than 0.5, that is less than alpha, and the calculated value will be more than 1.645. In other words, we will be rejecting the null hypothesis. Is the logic clear?
Yes.
So if the p value, so what we do is we compare this p value with alpha. If p value is less than alpha, the H0 must be rejected. Are you with me?
So if p value less than alpha, the null hypothesis will be rejected?
Yes, is less than alpha, H0 is rejected. Are you with me? Because if the P is less than alpha, naturally the red area is less than the blue area. So the calculated value of the test statistic is in the rejection region. So we are comparing the probabilities. P value is nothing but probability of having a sample which is as extreme or more extreme than the sample we have got. The sample we have got has resulted in the value of Z to be equal to 2.46. So I'm looking at the probability of having the sample to be having the test statistic to be 2.46 or more, which is nothing but my p value. So if I calculate my p value and if I compare with alpha, I know that as long as the p value is less than alpha, then your test statistic must be in the rejection region. So your decision is to reject the null hypothesis. On the other hand, if the p value is greater than alpha or equal to alpha, it doesn't matter. So greater than or equal to alpha, then H0 is not rejected. H0 is accepted. Are you with me? Because in this area, you do not reject H0. So in the white area, you don't reject H0. Whereas if the value is test statistic is in the rejection region, you will reject the H0. So smaller the value of P, more is the probability that H1 is true. Are you with me? Smaller the P value, more probable that H1 is true. Is it clear? Are you with me? Sarah, Ragad, Hala.
It's clear.
So the concept, I am trying to insist on the concept. So we are trying to find the p value, which is nothing but the probability of having the value of Z to be beyond your calculated value. So if the p value happens to be less than alpha, then we know that the test statistic must be in the rejection region. So we will be rejecting our null hypothesis. Are you clear? So if as long as p is less than alpha, H0 will be rejected. So if p value is greater than or equal to alpha, then you will be accepting the null hypothesis. In other words, you do not reject the null hypothesis. So this will be my decision rule if I know the p value. If I know the p value, then I can make use of this decision rule. If I can know the value of the probability of Z to be more than 2.46, which is nothing but my red area, that is the p value, what I can do, I compare this p-value with alpha. As long as p is less than alpha, we reject our null hypothesis. Otherwise, do not reject null hypothesis. Are you clear? So if this p-value is known, and this p-value will be known in case of softwares. If you use a software, we can get p-value using software. Let us say using SPSS. Are you with me? So if I can get the p-value, then my life becomes very easy. If I can get the p-value, what I can do, I just compare the p-value with alpha. Alpha, I know it is 5% or it is given in the question. So if we take it as 5%, let us say 0.05. So if the p-value is less than 0.05, I will be rejecting the null hypothesis. Otherwise, I do not reject null hypothesis. Just look for your p-value in the output and compare your p-value with alpha. As long as your p-value is less than alpha, you are rejecting your null hypothesis. If it is greater than alpha, you are accepting your null hypothesis. That is your decision rule. Are you with me? This eliminates the problem of remembering your formula, using your table, everything is gone. You need not calculate your test statistic. You need not go to your table and get your critical value. So you need not compare the test statistic with critical value for arriving at prediction. Only thing is, you identify where is your p-value. Look for your alpha. If p is less than alpha, reject H0. If not, do not reject H0. That is your decision. Are you with me?
Yes, so it's all computed.
Yes. So that is the advantage of having the p-value. P-value makes our life very simple. In other words, we need not remember the formula because we have got number of formulae. For each of the test, each type of test, we have got different formula which becomes more and more complicated, and we may have to use different types of tables. Maybe Z table, T table, chi-square table, F table, so many tables you will be having. So we need not bother about all these tables or all the distributions, and we need not worry about the formula for calculating your test statistics. When we can get the p-value straight away from the software, what we can do is we can make use of the alternate procedure for testing the hypothesis. What is the alternate procedure? Define H0, define H1. See whether it is a one-tail test or two-tail test. So there is no change up to here. Then define alpha. Alpha may be given, otherwise take it as 5%, 0.05. Analyze the data using your software, using your SPSS, and look for your p-value in your output. So get the p-value from the output. Are you with me? Are you with me? Get p-value. So it is given as SIG value. SIG, generally it will be two-tail. SIG two-tail value. Or simply SIG value. SIG means SIG two-tail, unless otherwise stated. Or it is called actual significance. Very clear? You will get the p-value or the actual significance from your SPSS output. So get this p-value, read out this p-value from the output, and compare this p-value with alpha. For a two-tail test, use as it is. SIG two-tail, if you have got the value, compare the SIG two-tail with alpha. And if SIG two-tail, that is p-value is less than alpha, reject H0. Otherwise, do not reject H naught. If it is a one-tail test, you consider half of P, half of two-tail test value. Are you with me?
Doctor,
Yes,
we
please.
can get B value also using Excel if we don't have SPS.
Some of them. Excel has got lots of limitations. Maybe I will try to show you.
Yes,
But
please.
not all of the tests can be done using the Excel. Lots of limitations and cumbersome and complicated. That's why SPSS happens to be very versatile and easy to use software. Okay. Okay, let me try to show that also. Okay, for one-tail test, use P to be equal to SIG two-tail divided by 2, half of that. Divided by 2. So take half of two-tail value, that will be the value for one-tail test. So you identify whether it is one-tail test or two-tail test using the alternate hypothesis. So you can make use of the P value for one-tail test to be half of your P value for the two-tail test. Are you with me? So your procedure becomes much simpler. So that is the procedure which we use. So let us try to, these things are given in your, okay, shall I clear? Let me clear this. The p-value provides information about the amount of statistical evidence that supports the alternate hypothesis. So what is the probability that the alternate hypothesis is true? So the p-value of test is the probability of observing a test statistic at least as extreme as the one computed, given the null hypothesis is true. So what is the probability of getting a value of Z which is equal to or beyond your calculated value? That is the value which you have computed. Are you clear? So it is the probability of observing a test statistic. So it is nothing but the value of Z which you have computed. So at least that value or more extreme than the value which you have computed. So let us see how to make use of this in our case, in this example. So you are given, we have calculated the Z value, the test statistic as 2.4615. So I am getting the probability of Z to be greater than or equal to 2.4615. So what is that value? That value happens to be 0.0069. Can you get that one? If you want, you can try. What is the probability of the Z to be greater than 2.4615? So look for your distribution, the Z distribution. The Z distribution, you look for the value the calculated value 2.4615 or 2.46, let us say. Okay. So what is the probability of having your test statistic to be 2.46 or beyond? So in other words, I am looking for the area beyond 2.46. Can you tell me what is the area beyond 2.46? Any of you? So what I do, I take the area between 0 and 2.46. And from 0.5, I subtract that, isn't it? What is the area from 0 to 2.46? Can you tell me? You have the table? The area between 0 and 2.46. Wada?
Null hypothesis.
What is the area between 0 and 2.46 in your Z table.
Area to reject the null hypothesis.
Yeah, if it is, no, what I am trying to look is, I am trying to calculate this probability of Z to be greater than 2.46. 2.46 is my calculated value, isn't it?
Okay.
So I'm trying to get this area, the probability of Z to be greater than 2.46. So for that, what I have to do, I will take the area between 0 and 2.46, and from 0.5, I subtract that area, isn't it? So what is the area between 0 and 2.46? Can you refer to table and tell me? Do you have the table with you? Z table? Or should I open?
%. No, it's 99%.
Okay, let me share the screen again. I am looking at the area under the Z distribution between 0 to 2.46. Do you want me to open the Z distribution table?
Yes, please, doctor, because I tried to look for the table. I don't have it on my computer.
Okay, let me stop sharing. Let me open that. Straight away, I cannot open it.
Doctor, it's 0.4931.
0.4931. Yes, you are right. Okay, so okay, let me share the screen again. Yes. Okay. Okay, can you see the normal distribution table? Can you see it?
Yes, doctor.
Okay, so what we are doing, we are trying to look for 2.46, isn't it? So
Yes, doctor.
go to 2.4. So I have got 2.4 here. So consider 2.4 here and 6, 0, 1, 2, 3, 4, 5, 6. So this is the value, 0.4931. Clear? So 0.4931 is the area under the curve between 0 and the value 2.46. So this area happens to be 0.4931. So what is this area? What is the area beyond 2.46? How do you get this one, this area?
The p-value.
Yeah, that is your p-value. So it is nothing but 0.5 minus, isn't it? 0.5 minus 0.4931. Are you clear? So what is the value you will get?
0.4431.
How come? 0.5 minus 0.4931. It is 0.00 something. It is 0.0069.
Yeah, yes, correct, doctor.
Okay. So it will be 0.0069. Is it clear to all? How we got this value? Any doubts? Anybody?
No, Professor.
Okay. So this is your p-value for our sample for the question we are looking at. So the p-value is nothing but the probability of z to be greater than our calculated value. The calculated value of z statistic was 2.46. So I'm getting the probability of z to be greater than 2.46, which is 0.0069. So this is my p-value. So when once I have got this p-value, what I have to do? I have to go in for our procedure. Let us say what was alpha. Alpha, let us say, is 5%. So compare p-value with alpha. 5% means 0.05. So compare this value with alpha. So whether 0.05 and 0.0069. So the p-value 0.0069, we know it is less than 0.05. So the p is less than alpha. So our decision is reject H naught. Is it clear? Are you with me? You just compare the p-value with alpha. So because p is less than alpha, we are rejecting the null hypothesis. If it is a two-tailed test, what we would have done? The p-value becomes double because the rejection region is on both sides. So the rejection region is on one side, on positive side, as well as on the negative side. So there will be two rejection regions. So if you have got a two-tailed test, the p-value would have been 2 times 0.0069. Are you with me? So 0.0069 on one side and 0.0069 on the other side. So you'll be taking it twice. Or if you are having the two-tailed p-value, you take half of it, you will get one-tailed p-value. Is it clear? Any questions, please?
So on the other side,
Yes.
it's gonna be 0069 is greater than 0.5, right?
On the other side, it is again the same. This is the probability. This is the area. The area is again 0.069. If I consider minus 2 point, let us say, if it is a two-tailed test, it will be plus or minus z, isn't it? There will be two rejection regions. So one value is 2.46. There will be another value which will be on minus 2.46.
Minus, yes.
So the area beyond minus 2.46 is also 0.0069, isn't it?
Yes.
So it will be 2 times 0.0069 for a two-tailed test. That will be the p-value.
Oh.
So in this example, it is only one tail because it is strictly greater than, mu greater than 170, isn't it? So it is a one-tail test, so we'll take only one side. If it is a two-tail test, you double it. You will get the p-value for the two-tail test. Is it clear? So what is our procedure now? Define H naught, define H1, see whether it is a one-tail test or a two-tail test. Define alpha. If nothing is given, alpha is 0.05. Get your p-value using your software. So compare the p-value with alpha. What is the decision rule? If p is less than alpha, reject H naught. Otherwise, do not reject H naught. For one-tail test, it will be p by 2. If p by 2 is less than alpha, reject H naught. Otherwise, do not reject H naught. That is all. So this will be the steps you will follow when you make use of the software, where the p-value is given. the basic advantage is that you need not have the calculations of test statistic to be made. You need not have the tables for arriving at your critical value. So the necessity of tables and the formula are eliminated. Are you clear? Yes or no?
Yes, doctor.
Okay. So note that smaller the p-value, higher are the chances that H1 is true. If p is small, the chances of H1 to be true is very high. If p is less than 1%, we can say that we have very high evidence, overwhelming evidence, which supports our alternate hypothesis. If it is between 1 to 5%, we can say that there is a strong evidence that alternate hypothesis is true. If the p-value is between 5 to 10%, between 0.5 and 10, 0.10 and 0.05, then we can say there is a weak evidence that H1 can be true. And if it is p-value is more than 10%, or if it is more than 0.10, then we can say that H1 need not be true. There is no evidence that H1 is true. So that's how we can look at the values for the p-value, and smaller the p-value, greater are the chances that the alternate hypothesis is true. Are you with me?
Yes. Is it as a general rule?
As a
Professor?
thumb rule,
Okay.
smaller the p, in general, smaller the p-value, H1, the chances of H1 to be true is very high. That is the rule. Okay. Any questions?
No question.
So, doctor, which one is the best? I mean, to reject the null hypothesis?
Yeah, to reject null hypothesis, our original hypothesis, H naught. What was our null and alternate hypothesis in our example? Mu is equal to 170 against mu greater than 170, isn't it?
Yeah. Yes.
So the same test we are carrying, we are doing it. So this null and alternate hypothesis are same. So based the alternate procedure, we are looking for a second procedure. What is the second procedure? The second procedure says that we look for our p-value. So we look for p-value and compare p with alpha. So because p is less than alpha, we reject H naught. So we say that we accept, let us say H1. What is H1? H1 was mu is greater than 170. So we accept our alternate hypothesis that mu is greater than 170. The same decision which we have arrived at by making use of the procedure of test statistics. The decision will be same. Only thing is, the procedure is slightly different. In the first procedure, we were calculating the test statistic using the formula, and then we were using the table to get the critical value, comparing the value of test statistic to the critical value to arrive at the decision. So the value of test statistic, what was your critical value? It was something like 1.964 or something, isn't it? 1.946. What was the value? 1.645, I think. Isn't it? So we are comparing the 2.56 with 1.645 because it is more than 1.645. We were rejecting the null hypothesis. Second method is we have got the value of the p. The p value happens to be 0.0069. Compare the p value with alpha. So because p value is less than alpha, we will be rejecting the null hypothesis. So the decision is same using any of the methods. But the second method is easier because we know the p value, just compare p with alpha. If p is less than alpha, reject H naught. That is the rule. Finish. So we need not go in for all the procedures of calculations and using the tables. Both will give you the same answer. Are you with me? Is it clear? Yes or no? I want your confirmation. If you are not satisfied and if you are not, let us say, if you have not understood it, then there is no point in all these things. Miss Hind, Hala, Khulud, Anahel.
It's clear, Professor.
Here?
Clear, yes.
Okay. So that is what is given in our slides. So let me share these slides now. Let us go back. So we are looking at the p-value, this p-value 0.0069. That's what we have seen just now. Clear? So we conclude that smaller the p-value, more statistical evidence exists to support the alternate hypothesis. So in this case, we have got the p-value to be equal to 0.0069. Compare the p-value with alpha, which is less than alpha. So we'll be rejecting our null hypothesis. That was the same decision which we had got here, rejecting the null hypothesis. Using our tables, we got the same result, and using our p-value also, we got the same result. Okay. So as a thumb rule, as I was telling you, the p-value, if it is less than 1%, you can say that there is a very high chances that the H1 is true, alternate hypothesis is true. If it is between 1 to 5%, there is a strong evidence that the alternate hypothesis is true. If the p-value is between 5 to 10%, there is a weak evidence. And if it is more than 10%, there is no evidence that the alternative hypothesis is true. So the p-value and rejection region method, the p-value can be used when making decisions based on rejection region method as follows. Define the hypothesis test and the required level of significance. So look for H0 and H1, see whether it is a one-tail test or two-tail test. Define your alpha. Perform the sampling procedure, calculate the test statistic and the p-value. So calculate the p-value, compare p with alpha. Reject the null hypothesis if p-value is less than alpha. Otherwise, do not reject the null hypothesis. Okay. So this is the procedure. State the null and alternate hypothesis. This is the steps in hypothesis testing using your software, SPSS, let us say. So using SPSS, state H0 and H1, see whether it is one-tail test or two-tail test. So if you want, you can add that also. See one-tail or two-tail. Okay, so this we will do making use of our H1. Look at H1 and see whether it is strictly greater or strictly less, it is one-tail test. If it is not equal to type, it is a two-tail test. So define alpha, calculate the actual significance, that is the p-value. So when once you get the p-value, make the decision. Reject the null hypothesis as long as p is less than or equal to alpha for a two-tail test. And p star less than or equal to alpha for a one-tail test. What is p star? P star is p by 2, where p is the value for the two-tail test. So that is your decision and that is your conclusion. So conclude, make a decision and interpret it in your normal terms so that you will be arriving at your conclusion. Are you with me?
Yes, Professor.
So these are the steps now, new steps for hypothesis testing, which is more compact, easier when we make use of the software. Just look whether alternate hypothesis is one-tail or two-tail. Define alpha, carry out your analysis, look for your p-value. P-value is SIG2 value. The actual significance, it is given as p-value or SIG2 tail. SIG2 tail or just SIG. So SIG value means the actual significance in your output. So look for your actual significance. If it is a two-tail test, just compare p with alpha. If it is one-tail test, take half of it and compare with alpha. As long as your p value is less than or equal to alpha, reject H0, otherwise do not reject H0. Okay. Is it clear? Any questions, please?
No questions. No.
Okay. So this is the procedure which we have seen for testing the mean. Means we have got a population or one population and we are trying to compare the mean of the population with a given value. So in the previous example, we had got the population of let us say the heights or widths, whatever it is, mu is equal to 170. So we are looking at whether the value of the average is equal to 170 or more than 170. In other words, we were having a population, we have taken a sample of 400 observations, and based on the observations, we want to see whether the mean has changed, whether the mean is more than 170. Are you clear? Are you with me? So we were having the situation of having one sample and taking a sample from the population for arriving at a decision.
Okay.
Okay. Okay. The other thing which we were having was the sigma was known. In the previous example, sigma was given, isn't it? The population standard deviation was known. If you look at the questions, sigma was known. The mean weight was 170 pounds with a standard deviation of 65 pounds. So this was our sigma, the population standard deviation. So because population standard deviation was known, we were making use of the formula x bar minus mu by sigma by root n, isn't it?
Yes.
Now, if sigma is not known, what will happen?
We will use the t-distribution.
T-test, you are right. So if sigma is not known, the formula changes to t-test. So that is the situation here. Inferences about population mean when population standard deviation is unknown. If population standard deviation is unknown, we make use of the t-test. The formula becomes x bar minus mu by s by root n, where we use the t distribution with n minus 1 degrees of freedom. So instead of using the z table, we have to use the t table. Are you clear? Otherwise, the procedure is exactly same. Let us look for our first procedure. What is the first procedure? Define h0, define h1, see whether it is a one-tailed test or a two-tailed test. Define alpha and use the table. So we use the t table with n minus 1 degrees of freedom for given value of alpha to get the critical value from the t table. Then use the formula t x bar minus mu by s by root n and calculate your test statistic. Compare your t test statistic with your t alpha, that is the critical value got from the table. So if the calculated value is more than the tabulated value from the table, you reject the null hypothesis. Otherwise, you do not reject the null hypothesis. The exactly same procedure. Are you clear?
Yes.
Okay, let us look at an example. The boys of a certain age have a mean weight of 85 pounds. An observation was made that in a city neighborhood, children were underfed. As an evidence, all 25 boys in the neighborhood of the age were weighed and found to have a mean of 80.94 pounds with a standard deviation, that is sample standard deviation of 11.6 pounds. So I want to see whether the mean weight has gone down because of underfeeding. Are you with me? Is the question clear?
Yes.
So we have got a situation where in a neighborhood, let us say in a locality in Bihar, the mean weight of boys was 85 pounds. So somebody says that in a particular locality, the boys are underfed. They are not given nutritious food. So what you want to do, you take a sample. You take all 25 boys in the neighborhood and you take the mean and standard deviation for these 25 observations. The mean for these 25 observations was 80.94 pounds and standard deviation for the sample was 11.6 pounds. So based on this sample, can you say that the average weight is less than 85 pounds because of underfeeding? Okay. Are you with me?
Yes. But
so what is the difference here? The difference is we are not given sigma, we are given the S. the population standard deviation is not given. Only the sample standard deviation is known. So what is the change we will have? The change is instead of Z statistic, we will use T statistic. Otherwise, the procedure will be exactly similar. So what will be our hypothesis? They are underfed, means the mean is less than 85. Underfed means the weight has gone down. So mu less than 85 against mu was equal to 85. So it is a one-tailed test. So we use the formula x bar minus mu by S by root n. So S by root n is nothing but standard error. So 11.6 by root of 25, you will get 2.32. So your test statistic happens to be minus 1.75. So this is your test statistic. Now we have to get your critical value from the T table. So how do you get it? We have got a sample of 25 boys. So the degrees of freedom becomes one less. So 24 degrees of freedom. So with 24 degrees of freedom, if you take alpha to be 5%, let us say the alpha, the level of significance is 5%. So we look for your T table for one tail test with degrees of freedom 24 and alpha 0.05. And that value you will get it as minus 1.71. Can you see that? You use the table and get it. Should I open?
Yes, I saw.
You saw that? Anybody having any doubt? Should I open the T table? Okay, let me stop sharing. Let me open that also. The T table. Okay, let me come back. Share the T table. Can you see this T table now?
We can see.
Oh, why it is not being shown completely?
But the numbers are.
Let me reopen again. Can you see the screen now? The
Yes,
distribution
yeah.
table. So what we
No.
are doing? Oh, again gone.
Yeah.
There is some issue. Okay. So what you have to do is you have to look for one tail test. One tail test, and the level of significance is 0.05. Okay. So look for your 0.05 as your level of significance alpha, and you are looking for your one tail test. Level of significance for one tail test 0.05. The degrees of freedom are in your first column. Go to your 24 degrees of freedom and corresponding to your 0.05 level of significance and get the value. Can you see this one now?
Yes.
Okay. So we are looking at one tail test alpha 0.05. Okay. and the degrees of freedom happens to be n minus 1, 24. So the value happens to be 1.711. Now this value is your critical value which you get from your table. Now note that the value will be negative, for it is a negative value minus t because it is a left tail test. The alternate hypothesis is mu less than 85, isn't it? So because it is less than 85, it will be negative. If it was mu greater than 85, it would have been positive. So because it is less than, the critical value will be on the left side, or the rejection region will be on the left side. So the value of t will be negative. So you will get it as minus 1.711. Very clear?
Clear, Professor.
Okay. So let us go back. So that's how we will get this value minus 1.71. So minus 1.711 or minus 1.71. So compare this minus 1.75 with minus 1.71. Is it less or more? Is it in the critical region, rejection region, or acceptance region?
We reject the null hypothesis.
Yes, minus 1.75 is less than minus 1.71. So we'll be rejecting the null hypothesis. So the decision is reject H naught at 5% level of significance. In other words, we can accept a null hypothesis or they are not underfed. So there is no evidence, there is no enough evidence to support the underfeeding of the children. Are you clear? Are you with me?
Sorry, doctor, again, what is the abbreviation of DF?
Of DF, degrees of freedom.
Okay.
Degrees of freedom. Degrees of freedom is n minus 1. So n in this case is 25. So n minus 1 is 24. The first column in the table, degrees of freedom. Clear? Are you with me?
Yes, Professor.
Okay, let us go to another example, maybe more realistic. In order to determine the number of pharmacists required to meet the demand, the productivity of newly hired trainees is studied. It is believed that trainees can perform more than 450 tests per day within 1 week of hiring. Can we conclude that this belief is correct based on productivity observations of 50 trainees? So we have got 50 trainees. It is believed that after giving a training for 1 week, the number of tests performed will be more than 450. So what I do, I take a sample of 50 observations, 50 people, and I take how much they have done, how many tests they have been done. First fellow, he will be doing, let us say 450, second fellow 465, third fellow 390, another fellow 500. So like that, I have got 50 observations. So based on the 50 observations, I have to test the hypothesis whether the trainees can perform more than 450 tests per day. So what are your hypotheses?
The null hypothesis is equal to 450 and the alternative is more than.
It is more than 450. Clear? Where did you get it from? Whether they can perform more than 450 tests. So your alternate hypothesis is mu greater than 150. Is it clear to all? So H naught is mu is 150, 450, and H1 is mu greater than 450. And we know that this is a one-tailed test. Are you clear?
Yes, doctor.
So we have taken a sample of 50 observations. So the degrees of freedom will be n minus 149. And your test statistic will be x bar minus mu by s by root n. So you are given 50 observations. You have to calculate the mean and standard deviation of these 50 observations. You can find it a bit difficult, isn't it? I want the value of X bar, I want the value of S, sample standard deviation. I don't know sigma. So I am just given the 50 actual observations. Very clear? So if I calculate, okay, let me say if I calculate, I will get the value of X bar as 460.38 and S as 38.83. So you can make use of the formula, the complicated formula. X bar is sigma X by N and S is sigma X minus X bar all square by N minus 1 under root. So you can calculate the value of X bar and S using traditional methods or using your Excel. If you use Excel, you can look for your, let us say, the values for mean and standard deviation, you can calculate, isn't it? Descriptive statistics. Are you with me?
Why don't we check the table?
Why don't we?
Why don't we check the table?
Which table?
The T
The
distribution.
table we use for getting our critical value. We check the table with alpha to be, let us say 5%, 0.05, and degrees of freedom to be 49, n minus 1. So we use the T table for getting your critical value, the rejection value, the rejection
Yes.
region.
1677.
Yes. So,
Okay.
but we want to have the test statistic. What is test statistic? Test statistic is X bar minus mu by S by root n. For this, we want to have X bar, we want to have S.
We don't have this information.
You are given 50 observations. Let me say you are given the 50 the data, 50 observations.
Okay.
So given the 50 observations, you have to calculate the mean and standard deviation. Very clear? You have got the raw data with you. That is what happens in reality. You will be having the raw data. We want to see whether the number of patients you are treating every day is more than, let us say, 500 or not. So what you do, you take a sample of, let us say, about 50 days. You see how many patients you have treated every day. First day, let us say 450 people. Second day, 600 people. Third day, 340 people. Fourth day, 550 people. So you'll be having the raw data with you. Are you with me?
Yes.
So given this raw data, you want to see whether the mean of this data is greater than a given value. That is what happens in reality. You will not be given X bar, you will not be given S or sigma, anything is not known. You have to calculate on your own as a researcher. So this is the real life situation which you will be facing when you are trying to test the hypothesis. You will be having the raw data. You don't know the value of X bar or S. You have to calculate them. Maybe there will be 100 observations, 1000 observations. So the manual calculations becomes almost impossible. Okay? Because the calculation of X bar and S is very tedious. If you can calculate then we can make use of the formula and you can get the value of T. X bar minus mu by S by root n. Knowing the value of X bar and S, I can calculate the T value 1.89. Now you compare it with your critical value 1.676. It is greater than 1.676, so we reject the null hypothesis. Things become simple only when you know the value of the test statistic, but calculation of test statistic itself becomes very cumbersome. So in these situations, what we do is we use our software. Are you with me?
We use our what?
Software, SPSS.
Yes, yes.
So what is happening here? We have got a population. From a population, we have taken a sample of size 50 observations. There is only one sample. Are you clear? We are taking only one sample of size 50 and you are trying to test for the mean, whether the mean is equal to a given value or greater than a given value. Is it clear?
Yes.
So this is the situation which you come across when you're testing for the mean for one population. There is a population. It may be population of these number of tests carried out, or the population of the weights of your patients, or heights of your patients, or number of patients you are treating every day, or the contents in a capsule, or the invoices you make in your pharmacy. So you have got a population where you are trying to take the mean against a given value. And you are taking a sample of size n, a single sample of size n, and based on this, you are carrying out the test. So this type of test where you use your t statistic, we call it as one sample t test. Are you with me?
Yes.
We call it as one sample t test because there is only one sample. Based on one sample of size n, we are arriving at a decision for the mean. So when you are given the data for these 50 observations, let us say the data is there in our file PROD. The PROD consists of actual values for these 50 observations, the 50 trainees. What is the output for the 50 trainees? So let me open the SPSS file and let us see how to proceed. Okay. Now let me open the SPSS file. Okay, can you see the SPSS file?
Yes, we can.
So I have given the variable, let us say the tests, the number of tests carried out per day. Okay. So the observations are there. These are the 50 observations, 1 to 50. So these are the number of tests carried out by the 50 trainees, 505, 400, 499. So I want to carry out the hypothesis test, whether the mean for these 50 observations is equal to 450 or greater than 450, isn't it? Are you with me?
Yes.
So I create my SPSS file by keying in the data, the test. So go to analyze and go to compare means. Analyze, compare means. In compare means, we have got different things. One sample t-test, independent sample t-test, paired sample, one way ANOVA. We have to select one sample t-test. Are you clear why it is so? We have got only one population and one sample of size 50. So we are comparing the mean with a given value. The given value in this case happens to be 450. Yeah. So such types of tests, we call it as one sample t-test. T-test because we use our t statistic. We have got the data with us, the raw data. It will calculate the mean and standard deviation, sample standard deviation, and use the t distribution table and the t statistic for calculation, and it will give you the p value as well as the t statistic. So look for one sample t-test, click on the tab, you will get one window which says one sample t-test. So we carry out the one sample t-test by selecting the variable. What is the variable? The number of tests. So this is the number of tests per day. So select this variable to test variable. There can be a number of variables. So we select the one which is important for us, for which we are trying to carry out the hypothesis testing. So click on the number of tests per day and push it to test variable. So now it tests for the number of tests per day. So it looks for this column. And what is the test value? U is equal to a given value. What is the value? The value was 450. So in this test value, you key in 450. Are you clear?
Okay.
So test value is 450. If you look for options, nothing to worry. Confidence interval, that is 95%. So it is looking for the 95% confidence interval or 5% level of significance by default. So click on continue and click on OK. So you will get the output in the new window. Can you see the output?
Yes, we can.
So here we have got The descriptive statistics, we have got N is that is 50 observations. The mean is 460.38. Sample standard deviation 38.827. Standard error of the mean sigma by root n. That is S by root n. 38.827 by root of 50. It will give 5.491. So these are all the descriptive statistics for the data we have got. Now comes the one sample test. The one sample test, the test value is 450. So you can check that whether you are given the correct value or not. So you are testing the mean to be equal to 450 against any alternative. So in this example, it is mu greater than 450. It can be less than 450 or not equal to 450. It doesn't matter. So here it looks for the mean to be equal to 450 against not equal to 450. Generally, it looks for a two-tailed test. So it looks for mu is equal to 450 against mu not equal to 450. So it gives you the t statistic. The value of t statistic is 1.89. The degrees of freedom is 49. The SIG value, this is our p value. So this is important to us. If you use the t statistic and degrees of freedom, once again you have to go back to your table and get your critical value from the t table and use the conventional procedure or procedure 1. But we can make use of procedure 2, where you can get the SIG two-tailed value, that is the p value for a two-tailed test. The p value for two-tailed test happens to be 0.065. Can you see that?
Yes.
So get this p value for the two-tailed test and look for your alpha, compare your p with alpha with, based on the type of test you have got, whether it is a one-tailed test or a two-tailed test. Note that in our example, we were having the one-tailed test, mu greater than 450. Are you clear? So because it was one-tailed test, the p value for one-tailed test will be half of the p value for two-tailed test. So the p value will be 0.065 divided by 2. So it will be 0.0325. Are you clear?
Clear, Professor.
So because our alternate was one tail, so the p value becomes 0.0325. Compare this with alpha, 0.0325 with 0.05. So 0.03 is less than 0.05. So p is less than alpha. The decision is reject H0. So reject H0 means accept H1. So H1, it says that mu is greater than 450. Are you with me? So this you can copy and paste. You can right click, copy, take it anywhere, and I think I have pasted it in your PowerPoint. So the same output. Okay, let me go back. Shall I go back?
Yes. We want to compare. Is it the same?
Yes, we have to compare. Okay. So here using the traditional method, we will be rejecting our null hypothesis. Now let us look for the p value. So this is the output we have got, isn't it?
Yes.
So this is the output we had got. So what we are doing now, we are looking for the p value. The p value is given here. This is for a two-tailed test. So the p value for one-tailed test, what will happen? So p value for one-tailed test.
We divide it by 2.
Yes. It will be 0.065. This is p value for two-tailed test divided by 2. This will give you 0.0325. And we know that this is less than 0.05 alpha. So what is our conclusion? So reject H0. Are you clear?
Clear, Professor.
So it is very simple. The same decision which we had made by using our all the procedure. So by looking at all the procedure, we had arrived at the decision that we reject the null hypothesis, isn't it? The same decision we are arriving at by just looking for your p value and comparing the p value with alpha. If you want, you can take these values of t. T is 1.89 and degrees of freedom 49, the same values which you have got here using the formula. So 49 degrees of freedom, the calculated value of t statistic is 1.89. Are you clear? So if you use that, once again, we are going back and making use of the traditional T table. So if you lose your P value, you need not have your T table, you need not remember the formula. Straight away, you can arrive at your decision. Are you clear?
Clear. Yes.
Sometimes you wanted to see the Excel also, isn't it? Let me show
Yes,
you.
because we don't have SPSS.
Yeah. Excel. Okay. Let me open the Excel file. Okay, can you see this Excel file?
Yes.
So this is the data we have got. The 50 tests you have got. Again, you have keyed in the data here in column A. The 50 observations, the raw data. Okay. Can you see this?
Okay. Yes.
What I do is, I have to make use of the test statistic. Okay. So how to calculate test statistic? X bar minus mu by S by root n. So what I do, first of all, I calculate the descriptive statistics. So click on data, go to data analysis, and go to descriptive statistics. Click on OK. So select the input range. It is from A2 to A51. Okay. Click on OK. You will get the output. Oh, sorry. You have to look for your summary statistics and confidence levels. Okay. And click on OK. So you will get the output in a separate sheet where you have got the descriptive statistics. Are you with me?
Yes.
So here we have got the mean for these observations, 50 observations, the standard error, S by root n, the standard deviation, okay, and the number of observations is 50. So you have to use this data and you have to calculate the test statistic. That is first thing you have to do. So it may be something like this. I have made use of the same thing. This is your X bar. This is your S by root n standard error. This is your number of, the count is number of observations. And our hypothesis is mu equals 450 against mu greater than 450, which is a one-tailed test. Okay. This is our test statistic. So we have to calculate our test statistic. What is test statistic? It is X bar minus mu by standard error. So it is B3 minus B17 by B4. So use the formula. Are you clear?
So we have to write the formula.
Yes, you have to write the formula and calculate the t value.
It does. It's not built in the Excel.
No.
Okay.
Okay. And you can get the tabulated value from the table. You can compare your tabulated value with the critical value. 1.89 is more than 1.67. So you are rejecting your null hypothesis. You can get your p value. If you want, you can get your p value from the t distribution using your calculated value. You have calculated the value of t, isn't it? Using the formula. Are you with me?
Yes.
So you can get the p value for one-tailed test. You have to use the formula equals t dot distribution, that is t dot dist dot rt. Rt means right tail. With the value 1.89, which you have calculated with 49 degrees of freedom. So this is the formula you have to use. equals T dot dist dot RT bracket the T value which you have calculated 1.89, comma the degrees of freedom in this example 49.
Yes.
Are you clear?
It's yeah.
So you will get the value, the P value that is from the Excel. Now you compare this P value with alpha. So 0.032, the same value which you had got, 0.0325, if I remember, isn't it? This is for one tail test. If you want for two tail test, the formula will be T dot dist dot 2T. 2T means two tail. In brackets, the T value 1.89 with degrees of freedom. So that will give you the P value for two tail test, which is basically twice the P value for one tail test. So for one tail, it is RT, right tail. If you have got less than, strictly less than, mu strictly less than 450, you have to take the value that which will be same point, whether it is right tail or left tail, because it is the probability will be having the T distribution right tail value to be equal to the left tail value. Whereas for a two tail, it will be twice this value. The P will be, or you can make use of the T dot dist dot 2T, two tail. Otherwise, RT means right tail, one tail. So that's how you can get the P value using your T value, which you have to calculate. This you have to calculate using your descriptive statistics, using our traditional formula. So using this value of T, you can get the P value. Now compare this P value with alpha. Very clear? So this is less than alpha. So reject, it's not. So that is our decision.
Okay.
So that's how we use the Excel.
Clear, Professor.
Okay, any questions?
No, no question.
So that's how we carry out the one sample T test using the SPSS as well as Excel. Yeah. So if you want to carry out the same one sample T test for proportions, population proportion, we know that the population, if you have got a binomial distribution, if NP and NQ are greater than or equal to 5, then we can approximate it by a normal distribution. So we can make use of exactly similar procedure, only the test statistic will be Z, which is P cap minus P by root PQ by N. Very clear?
Yes.
Nu is NP, not P. Nu is NP and sigma square is root PQ by N. So make use of the formula. The formula will be Z is P cap minus P by root PQ by N when NP and NQ are greater than or equal to 5. So let us look for an example. A pharmaceutical company claimed that its medicine was 80% effective in relieving the allergy for a period of 15 hours. In a sample of 200 persons who were given the medicine, 150 persons had relief. Do you think that the medicine was effective in less than 80% cases? Use 0.05 level of significance. Is the question clear?
Yes, the effectiveness of the
The
medication.
effectiveness of the medicine, he says it is 80% effective. 80% means 0.08, the proportion of people who are getting relieved. So you are taking a sample of 200. Out of the sample of 200, 150 had relief. So this is your, let us say, X. So your P cap will be, what will be your P cap? It will be X by N, isn't it? The proportion of people who have got relief. out of 200 people. P is 80%. P is 80% or 0.08, and P cap is 150 by 200. Very clear?
Okay.
So what is 150 by 200?
Uh, 0.75.
0.75. Okay. So this will be 0.75. So given the value of P is 0.80. Okay. And P cap happens to be 0.75, and your alpha happens to be 0.05% level. So this is your alpha. So what is the procedure you will follow? Define H0, define H1. So what is the null and alternate hypothesis? Do you think that the medicine was effective in less than 80% cases? So what will be your hypothesis?
The null hypothesis
Yes.
Less than 80.
equal the
P
null.
is less than 80. Is it null hypothesis?
Less, it's the alternative hypothesis.
It is alternative hypothesis. Are you clear? So the alternate hypothesis happens to be strictly less than 80% or strictly less than 0.8. So the null hypothesis opposite of that, let us say it is greater than or equal to 0.8. Doesn't matter. So these are our null and alternate hypothesis. Is it one tail or two tail?
One tail.
This is a one tail test because it is strictly less than. Okay. So now we can make use of our test statistic as P cap minus P by root PQ by N when NP and NQ are greater than or equal to 0, greater than or equal to 5. So if you want, you can test it. The value of N is 400, or how many, what are the sample size? What is value of N?
200.
200. So N is 200 and P happens to be 0.8. So you can find out what is NP and NQ. So NP happens to be 200 times your 0.8. 200 times 0.8 is how much? It is greater than 5, isn't it?
Yes.
160. And NQ will be 40. It is also greater than 5. So we can make use of our Z statistic. So what is our procedure? Define H0, define H1, which we have done. Define alpha. Alpha is given to be 5%, 0.05. And NP and NQ are greater than or equal to 5. So we can make use of Z distribution. So look for your critical value for 5% level. So the critical value using your Z table, you will get it as minus 1.645 because it is strictly less than, note that it will be negative. Are you clear?
Okay.
So your critical value happens to be minus 1.645. So this will be your alpha. Now what is our next step? Calculate the test statistic. Test statistic is given by Z, which is P cap minus P by root PQ by N. You know all the values. P cap was 0.75. That was nothing but the ratio of 150 to 200, 150 by 200, which we had calculated earlier. So it was 0.75, P is 0.8. So substitute the values, N is 200. You will get the value as minus 1.786. Compare your Z statistic, that is critical value, with the test statistic. The minus 1.786 is below your minus 1.645. So what is your conclusion?
Reject the null
So we
hypothesis.
reject the null hypothesis. Since the calculated value Z is less than the critical value, we reject the null hypothesis. and conclude that the claim of the company that the medicine is 80% effective is not justified. So reject null hypothesis means mu is less than 0.8. So your claim that it is effective in 80% of the cases is not correct. So that's how we can make use of the Z statistic for testing for the proportions. Is it clear? So here we have to go through only the traditional method. No SPSS for this. Proportions, not very common usage. So the usage is more for the mean. So we have got the SPSS methodology for comparing the means. Are you with me?
I'm lost here.
Where were you last? We are using procedure 1.
No, about the statement.
The last statement, the decision.
We reject the null hypothesis.
Yes, you know that we are rejecting null hypothesis. What is your null hypothesis? The null hypothesis is this, isn't it? So we are rejecting your null hypothesis. So we are rejecting your null hypothesis means we are accepting your alternate hypothesis, which says the proportion of patients is less than 0.8. So what was your claim? The claim is that, do you think that the medicine was effective in less than 80% cases, which we reject?
It's not effective in less than 80%.
Yes. So that's what is the decision.
Okay.
So we conclude that the claim of the company that it is medicine is effective 80% is not justified. It is not 80%, it is not justified. Clear?
Okay. Yes.
It is less than 0.8. Any questions, please? So these are the types of tests which we come across when you are comparing the mean of a given population with one value. Mu is equal to a given value or P is equal to a given value with all alternates, let us say greater than or less than or not equal to. Greater than or less than will give us one-tail test, not equal to will give us two-tail test. Now this particular methodology is extended. We'll concentrate more on our means. So instead of comparing one population mean with a given value, we can compare the means of two populations. Let us say you have got two clinics, one in Riyadh and one in Jeddah. You want to see whether the average number of patients who come to you in a day in Riyadh and in Jeddah, they are same or not.
Okay.
So you are having two populations. One population as patients of Riyadh, one population patients of Jeddah. There are two independent groups, different groups. And you are trying to compare the means for these two different groups. So what will be your hypothesis? The null hypothesis says the two means are equal. There is no significant difference in the means for the number of people in Riyadh and number of patients you are testing in Jeddah. If you say mu1, group 1 as Riyadh, group 2 as Jeddah, then the null hypothesis can be mu1 is equal to mu2 against all the alternates. Alternates can be mu1 greater than mu2 or mu1 less than mu2 or mu1 not equal to mu2. Are you with me?
So it's two-tail.
So if it is not equal to, it is two-tail. Mu1 greater than means one tail. Mu1 less than mu2 is one tail.
Okay.
So what is happening is you are comparing the means for two populations, mu1 and mu2. So your hypothesis is based on two samples. You take one sample from Riyadh, let us say N1 people, another sample from Jeddah, N2 people, let us say 100 people in Riyadh and 200 people in Jeddah, or 100 and 100, it can be same or different. So based on these two samples, we will calculate the mean for first sample, mean for second sample, standard deviation for first sample, standard deviation of second sample, And then we have got a formula for arriving at the t value, which is quite complicated. Are you with me?
Yes.
But the idea behind that is you are comparing the means for two independent groups. So that situation, we call it as two independent sample t-test. We are comparing the means for two independent populations. So the type of test we carry out, we call it as two independent sample t-test. We are not interested. I won't give you the formula. I won't give you the tables methodology. In all these procedures, the formula are more complicated. Let us not worry about it. And it is more time consuming also. So what we do is we will make use of the software. We make use of the software and we proceed using the p-values.
Okay.
So that we can avoid the formula, we can avoid the table, we can avoid the distributions. But you must be very clear that when to use which type of test. We use one sample t-test when we are comparing the mean of a population with a given value, where you are taking only one sample. When you come to two independent sample t-test, you are comparing the means for two different populations, independent groups. Are you clear?
Yes. So we do a different procedure.
We do a different procedure.
Okay.
Or if you use the p-value procedure, it will be very similar. Define H0, define H1, see whether it is a one-tailed test or a two-tailed test. Define alpha and get your p-value from the output of the software. Compare p with alpha. If p is less than or equal to alpha, reject H0. Otherwise, do not reject H0. Exactly same procedure. The software will take care of the formula. It will take care of the distribution. It will give you the p-value. Just look for your SIG value and compare your SIG value with alpha. But you must know that you are applying a two sample t-test, two independent sample t-test, where you are comparing the means for two different populations. Is it clear?
If I don't have the software, I do it like one sample t-test for two.
Yeah, for that you need to have the formula. You need to have a different formula.
Different, okay.
Yes, different and more complicated. That's why I don't want to give you.
Okay.
So as you go deeper into the subject, you will get more and more complications. The formula becomes more and more complicated. The procedure is same. So there is no point in going on calculating using the formula and making the calculations. Are you clear?
Yes.
So I will show you how to make use of the software SPSS. You can go to lab, or you can get if you have the software, you can make use of it and you can arrive at the p-value. So this is a situation where you are comparing the means for two independent groups. So I'm calling it as two independent sample t-test, where we make use of a t-distribution again and we arrive at a decision. Now, compared to this independent, why I am making this particular statement independent? There is another one where we are comparing the means for two dependent samples. We call it as two dependent sample t-test or paired sample t-test. Can you think of a situation where you are comparing the means for two samples from the same population? Can you think of an example?
I'm sorry, Professor, I didn't hear the question.
you are clear about two independent sample t-test, where you are having two independent populations, two different populations. Very clear?
Yes.
And
So-
you are comparing the means for two different populations. You are
correct.
comparing the mean height of a citizen of Saudi Arabia with mean height of a citizen of America. So you take a sample of 1,000 people in Saudi Arabia, and you may take about 1,500 people in US, and you arrive at the heights and compare the means. If mu1 is the mean for Saudi Arabia group, mu2 for US group, so the hypothesis is mu1 is equal to mu2 against any of the alternative, mu1 greater than or less than or not equal to mu2. Isn't it?
Okay. Yes.
Now, I have got another situation where you are comparing the means for the same population. You are having two samples from the same population, and you
Okay.
want to compare the mean. Can
And
you
this is
arrive at-
different.
can you think of such situations?
So if we have one hospital,
Okay,
but two branches.
two branches. Okay,
Yes. Maybe the height of branch A and the height.
yeah,
guess
there are
the
two
height-
different populations. Again, it is two different groups. Two branches are in two different locations, isn't it?
Okay.
So it's
How about the same branch but female and male?
female is one population, male is another population. So you are taking samples from females, you are taking samples from males. So they are independent groups.
Okay. I don't know.
Okay. So let me give an example. Let us
Okay.
say you are hiring, let us say you are having some technicians with you who will be carrying out the analysis. You want to improve their performance. So you give them some training, 1 week's training program. You want to see their productivity after training. So you have got a group, let us say about 50 technicians. The performance of these technicians before training and after training. You want to compare the means.
Okay.
So you have got the same sample, the same 50 technicians, you are taking observations once before training, once after training. Very clear?
Yes.
So you will be having two observations for the same person. One is before training, another is after training. So
Yes.
we have got pairs of observations for each sample. That's why it is called paired sample t-test. Dependent sample t-test or paired sample t-test. Because you will be having two samples for the same, two observations for the same sample. So you are comparing the mean of performance before training, let us say mu1, and performance after training, the average number of tests they carry out after the training. So your null hypothesis says the training is not effective. mu1 may be same as mu2. Or you want to see whether the training is effective or not. mu1 is less than mu2. Or mu1 not equal to mu2, or mu1 greater than mu2. Are you clear?
So this is a two dependent.
Yes, this is an example of two paired sample t-test or
Oh.
dependent sample t-test.
Okay.
So we have got two samples from the same population, same sample at two different situations. Observations for the same sample. The sample remains the same. So if you are comparing the means, once again you are comparing the means before and after, mu1 and mu2. So you are looking for the difference. mu1 is equal to mu2, or mu1 minus mu2 is equal to 0, or mu d is equal to 0. The difference between mu1 and mu2, if I call it as mu d, then mu d is 0, or mu d not equal to 0, greater than 0, less than 0. So this will be my hypothesis. So there we have got a different procedure, a different formula, and a different methodology. So once again, what we do, we define null hypothesis, we define alternate hypothesis, see whether it is a one-tailed test or a two-tailed test, and then we make use of the software and make use of the two paired sample t-test, a paired sample t-test or dependent sample t-test. Very clear? And
Yes.
arrive at our p-value and compare p with alpha. And if p is less than alpha, reject H naught, otherwise do not reject H naught.
Okay.
So if you make use of the traditional methodology, there is a different formula. We have to calculate the differences, we have to look for the averages, then make use of another formula for calculation of the t statistic, and then use your t table and arrive at the decision, which becomes more and more complicated. As the sample size increases, the amount of calculations becomes heavy. So what we do, we look for our p-value and compare p with alpha to arrive at the decision. So that is another situation where we will be comparing the means for two dependent groups. Dependent groups means same population, two samples taken from the same population. So when we are comparing the means, two means, so there are two types. One is independent samples, one is dependent samples. In independent samples, we are comparing the means from two different populations, whereas in paired sample or dependent sample, we are comparing the mean at two different situations from the same sample, from the same population. So this you must be very clear. So you have to select the type of test from the analysis which you carry out using your SPSS or your software. It will not say which type of test you have to carry out. It won't say whether it is one sample t-test or whether it is a two independent sample t-test or whether it is a paired sample t-test. Depending on the situation, you must be able to select the right type of test. Are you with me?
Yes, we have to know exactly what.
Yes. So that is the knowledge which you must gain. You must know whether you are using one sample t-test or whether you are using independent sample t-test or whether you have to apply paired sample t-test. So this is a situation when you are comparing the means for two populations. Now this can be extended. What happens if you are comparing the means for three or more populations? Let us say you have got the clinics in three locations, one in Riyadh, one in Jeddah, one in Dammam, one in Taif, one in somewhere else, Makkah, one in another one Medina. So there can be three or more populations. Are you with me?
Yes.
So you want to compare whether the average number of patients you treat every day in all these locations is same or not. So if you have got k locations, k to be greater than or equal to 3, you can say mu1 equal to mu2 equal to mu3 equal to mu4 equal to mk. That is your null hypothesis. Means the number of the sample, the population mean for the k groups, k independent groups are equal. So what will be your alternate hypothesis?
We will compare between the null.
Yeah, null hypothesis is mu1 equals mu2 equals mu3 up to mu k is equal to mu k, where k is 3 or more. Okay.
Okay.
So what will be your alternate hypothesis?
Is it equal Q? We put the number, and if it's not equal to it, then this is the alternate hypothesis.
Not equal to.
Not equal to.
You see this one? You are comparing the means for 3 or more populations. Okay. So if you compare the means for 3 or more populations, we use what is called one-way analysis of variance. So a different technique. ANOVA is called one-way analysis of variance. So what is your null hypothesis here? The null hypothesis says mu1 equals mu2 equals mu3 up to equal to mu k, where k is greater than or equal to 3. Let us say, as an example, I will take only 3. Mu1 equals mu2 equals mu3. Okay.
Okay.
My H naught is mu1 equals mu2 equals mu3.
Sorry, doctor, apologize. We have a lecture after that. We only
Okay.
have 2 minutes break.
Okay, no
Apologize.
problem. Let us take up this issue in our next class. Please think over. So the alternate hypothesis, we cannot say not equal to, not equal to. It is not correct. We cannot put not equal to. Only 2 may be equal, other may be not equal. So the alternate says not all the means are equal. There is at least one mean which is different from the others.
Okay.
Okay.
Yes.
Anyway, let me take up this one in our next class. So let us stop here for today. And I will give you examples of how to make use of our software for each of the situations. Come to independent sample, paired sample, and ANOVA, all these things. I have given you one file on SPSS with examples, SPSS output with examples. So maybe you can download that one from the LMS and you can bring them. We will go through them also in our next class. Okay.
Inshallah. Thank you, Professor.
Okay, please. We'll stop here for today. Thank you. We'll meet again next Saturday, same time, 10 o'clock.
Thank you, doctor.
Thank you.